Hello everyone, I'm pleased to be here today to present my work on mechanical and thermal expansion property of injected wood polymer composites. So this work was carried in the laboratory of composite material for construction under the supervision of Professor Emmanuel Ferrier and Alain Serrani. So in this presentation, I will begin with a brief presentation of the project. Then I will present tensile and bending results. After that, X-ray tomography results and fiber efficiency. Thank you. And fiber. And fiber efficiency. Then thermal expansion results, and finally conclusion and perspective. So, the purpose of this project is to develop a biocomposite material based on polypropylene matrix reinforced by wooden fiber. So, we used two types of wooden fiber. One with 200 microns particle size, and the other with 1 millimeter particle size. And the wooden fiber comes from sawdust wastes of various tree species, and the polymer used is the recycled polypropylene. So, and the purpose is to manufacture external cladding panel for buildings. So, wood polymer composites has many advantages, like good mechanical properties, no insect damages like wood, and we can manufacture complex shapes by injection. And this material can be used in various domains, like cladding panels and even indoor trims for cars. So, in this project, several mixtures were prepared using a combination between the two types of fibers, the 200 microns and the 1 millimeter. And I choose to present this 5 mixture in this presentation. And for mixture 3 and 5, for example, with 50% of fiber in fiber rate, we added a compatibilizer, which is the PPGIM. In order to see his effect on the mechanical properties and on the adhesion between the fibers and the polymer. So now I will present you tensile and bending results. So we can see here that the trend is almost linear, whatever the type of mixture. The tensile and bending modulus increases with an increase in fiber rate, and with that, the composite changes from ductile material to a brittle one, and we can see that in the decreasing in the tensile and bending resistance. So, measuring the transversal deformation, we were able to calculate the Poisson's ratio, which is equal to 0.35 for this composite. And seeing the different curves, we can conclude that this Poisson's ratio is independent of the type or content in fiber, and also we noticed the initiation of the damage of the composite, which is marked by the loss of proportionality between the transversal and the longitudinal deformation, and which occur at between 30 and 50% of maximum resistance of the composite. So we added 3% of PPGIM, which is a compatibilizer, in the mixture 3 and mixture 5 with 50% of fiber rate. So we noticed that his effect is he has a negative effect in the tensile modulus, and the tensile and bending modulus, and a positive effect on the resistance. So we noticed decreasing between 15 to 16% in tensile modulus, and between 16 to 21% in bending modulus. And for resistance, we noticed an increasing between 36% to 45% in tensile, and between 77 up to 102% in bending. In fact, polypropylene polymer is formed with linear chains. So he has a relatively high crystallinity degree. So adding a compatibilizer such as PPGIM decrease the crystallinity degree of the polymer, and that induces the loss of modulus. And this hypothesis will be confirmed soon with the DSC measurement that allows us to calculate the exact degree of crystallinity of the composites. And so for further understanding of this composite, we used the X-ray tomography technique. This technique allows us not only to see the fiber distribution, but also to calculate the fiber fraction and void fraction in the sample, and also to measure the fiber length and diameter in the sample. And the sample used by this technique is the same used in the bending tests, and the resolution used here is between 5 to 6 microns depending on the mixture. So X-ray tomography result is presented in form of raw images. In these raw images, we can see the different components of the composite, the fibers, the polymer, the matrix, and also the voids. So, processing these raw images, we can isolate fiber only or voids only, depending on what we want to see. And we can do a 3D reconstruction of fiber distribution or void distribution also. So, here is an example of fiber distribution of mixture 1 and 2 with 10% in image A and 50% in image B for mixture 1, and 10% and 50% for mixture 2. And we can notice here that for mixture 2, with the one with the 200 microns particle, the distribution is more homogeneous in the volume. So, and that can be explained by the lower viscosity of this mixture in the injection phase. And we were able also to reconstruct a 3D model of the fiber distribution for this mixture. So the idea here is to compare the same mixture, which is, for example, here mixture 3, with and without the PPGIM. So without the PPGIM in image B, we notice the existence of gap between the fiber and the polymer. This gap testified that on the pore addition between the polymer and the fiber. And adding only 3% of PPGIM, we notice that the gap is no longer existent in image C, and we can consider that the polymer and the fiber is perfectly merged. So, in fact, we can conclude that adding a compatibilizer such as PPGIM can solve the compatibility problem between the polymer and the fiber by adding a chemical band between the hemicellulose of the fiber and the polymer, the polypropylene chains. So, using also a 3D model of the voids distribution, we were able to plot the voids distribution in 3 directions. So, direction X, Y, and Z. And we noticed that the voids are located in the center of the sample, and it's almost constant through the direction Z, through the Z direction. And we were able also to measure the real length of fiber and the diameter of fiber and the volumic fraction of fiber and the voids in all the symbols. So, with the help of X-ray tomography, we were able to have many parameters like volumic fraction of fiber and voids, fiber distribution and void distribution, also fiber length and diameters. So using those different parameters, we were able to inject those parameters in an analytic model to calculate the efficiency of the fibers. So in order to do that, we used a simple model established from the law of mixture, which is the Cox model. So in this model, we are searching for alpha, which is considered like fiber efficiency. Alpha here is calculated using all the parameters calculated or determined using the X-ray tomography technique. So we found that the efficiency of the fiber decreases with the increase in fiber rate, but it tends to be constant. So now I will present you thermal expansion results. So this test consists on putting the sample in a climate chamber, controlled climate chamber, and then applying the desired temperature range, which is in this case from minus 25 degrees to 60 degrees Celsius. And then record the longitudinal deformation of the samples due to temperature variation. So we were able to plot the strain temperature curves, and these tests were repeated 3 times on the same samples. So seeing those curves, we noticed that the slope increased between the first and second test, and this can be explained by the degradation of the addition between the fibers and the polymer due to the polymer deformation due to temperature variation between the first and second test, and then it will be stable. So using those curves also we were able to calculate the linear thermal expansion of the composite, and we noticed that this coefficient decreases with the increase in fiber rate, and this can be explained simply by the lower thermal expansion of the wood fiber due to temperature variation. So to conclude, we can say that tensile and bending rigidity of the composite is proportional to the percentage of reinforcement. The small size fiber have more homogeneous distribution in the volume, and we can also conclude that increasing the fiber rate decreases the thermal expansion coefficient. And this study is just an initiation on the development of the external cladding panels, and must be followed by further tests like aging test, water submersion, and wind tests and impact tests which we are preparing now. And also we are intending to prepare a numeric model of the panels to simulate their behavior using different type of attachment on the wall with the properties found by experimental tests. Thank you for